Hello class, this is Mr. Eggleston and this is Algebra 1, Lesson 5.5, titled From Sequences to Functions. What this lesson's about is going to relate this idea of a sequence which we've seen, right? It's just a list of numbers, an ordered list of numbers. How we can relate that to this concept of a function where each input goes to only one output. So what we're going to do is understand that sequences are a special type of function that assigns to each number in the sequence n, which is a term value, f of n. All right, the domain of this function, and this is kind of important, is the positive integers. They're talking like 1. Oh, wow, that's fat. They're talking 1, 2, 3, like that. Okay, positive. Not negative, like -1, -2. And not decimal, like 1.2 or 1.3. We're talking integers. 1, 2, 3, 4, 5, 6. Those numbers represents the location that term is in the sequence. Another learning target is we're going to learn to use function notation to write a rule for the sequence. This is going to be rather straightforward, but the notation is going to look confusing, and I don't want you to be confused about it. All right, because here's the notation. We're going to use notation f of n plus 1 and f of n minus 1 to represent the next and previous terms respectively. That is in reference to n. So f, oh wow, that's too small. Let's do that. So f, if you have f of n plus 1 is the next term in the sequence ahead of it, and f of n minus 1 is the term right behind it. So if you had a sequence of numbers, and again, this is just a sequence of numbers, if we had like 1, 5, and 9, all right? And let's go with 13, and then just keeps going, all right? If our focus is on, and this is the first term, the second, the third, the fourth, all right? So if we call this 5 f of n, if we call that f of n, this would be f of n minus 1, the one right before it in the sequence, and this term would be f of n plus 1, which is the term right in front of it. And if you wanted to do it and get really fancy, you could call this one f of n plus 2. Again, remembering that f of n is the second term. Okay? That's the way this notation works. So if n is 2, n minus 1 would be 2 minus 1. That would be referring to f evaluated at 1, which is this number 1. Right here. Okay? Now, let's go into here. So, oh, did I answer? Yeah, we did. All right. So, the first 4 figures of a visual sequence are shown below. How do you see the pattern growing? All right. So, let's look at this. We have 3 here, 6 here, 1, 2, 3, 12 here, and 24 here if you count this, right? 3, 6, 9, 12, 15, 18, 21, 24. So figure 4 is 24, figure 3 is 12, figure 2 is 6, and figure 1 is 3. Those are the numbers in the sequence, represented by these dots. Okay. How do you see the pattern growing? Well, you could literally say each column. Oh, wow, I don't know why I put an F in there for C. Column consists of 3 dots. Okay. The number of columns of dots, columns of dots, is doubling, right? What does it mean to double? It means you're multiplying by 2 each time. Okay? So, the total number of dots doubles also. Okay. Don't worry about the covered up stuff. Those are the notes, the side notes that I'm going to show you after we go through this activity. Now it says complete the the table given on the right. So when n equals 1, there were 3 dots. When n equals 2, there was 6 dots. When n equals 3, there are 12 dots. And when n equals 4, there are 24 dots. And if you want to keep going, 5 would be 48 dots. 6, 96 dots, because we're just doubling each time. Is f of n a linear function? How do you know? Well, let's look. Linear means that you're adding the same amount each time. So as we go from 3 to the next, from the first term to the next, we start with 3, and then we go to 6. So if it was linear, we're adding 3, which means we should be adding 3 here. But lo and behold, we're not. We're adding 6. It's not a constant rate of change. So it is not linear. Okay? No. The number of dots isn't linear. Okay? Or I shouldn't say that. Isn't going up by the same amount each time. We're not adding the same number. Okay, the number of dots isn't going up by the same amount each time. From one value of n, from one figure to the next. Okay? Because of that, it is not linear. However, we do know what kind it is. It's geometric, because we're multiplying by 2 each time, but we're going to get into that. All right, now it says C. Again, you should be doing this on your own, then coming back and seeing what I wrote. Find f evaluated at 5. Well, I just did it. It's 48. F of 5 equals 48. And what is the meaning of this? This represents, this means that the fifth figure has 48 dots. Okay. Now, if we know that f of 8 equals 384, and we realize that to go from one term to the next, we're actually doubling it, multiplying by 2 each time, right? Like 12 multiplied by 2 is 24. 24 multiplied by 2 is 48. And they want the 8th term, we just keep going. So if the 5th term is 48, the 6th term is 96, the 7th term would be 90 would be 180, 192, and the 8th term would be double 192, which is 384. So the 9th term, f of 9, is just equal to 384 times 2. And that works out to be 768, because we're just multiplying by 2. Now they're saying on question 4, if you know what f of 12 is, which is equal to, or f of 12 equals 6144, then f of 11, since we have to multiply to get to 12 by 2, to get from 12 to 2, or 11, excuse me, we have to divide. So to go this direction, we divide by 2. And you end up with 3072. It's too tight. Sorry about that, kids. There we go. 3072. And how did I get that? I just took 6144 and divided by 2. Okay. So the next question talks about, if you know f of n, how would you find f of n plus 1? You would just double f of n, which, or multiply, because that's what doubling means, multiply f of n by 2. All right? So let's go back and I'll uncover some of the things that were written and we'll discuss it. First of all, what this is saying is that the number of dots depends on, or is a function of, the figure number. That's the first thing you should realize. The number of dots depends on, which means it is a function of, that's, you notice it's in a different color, the figure number. All right? Also, the figure number determines the number of dots. That's, if you know the figure number, you know how many dots are in there. Pattern represents a geometric, not arithmetic growth, because we're not adding the same number. We're actually multiplying by the same number. So pause this and write these red pieces down into your notes, onto the document. All right. So remember, we did look at geometric functions as compared to linear or arithmetic functions. And the difference is arithmetic, you add the same number. And geometric, you're multiplying by the same number. And we called that the common ratio. In this case, the common ratio R was 2. R equals 2. And that's the common ratio. So I'm trying to bring back some of the language from previous units, lessons, all right? Also, this notation means that f of n, this right here, is the nth term. The nth term. Likewise, the f of n plus 1 is the n plus 1th. I know that's a weird way. It's the n plus 1th term, which equals the next term. So this would be like the current term, we could call it. And this over here is the next term. And the n plus 1 inside just means we're increasing the input by 1. We're going to the next one higher term in the sequence. And that's what that means. All right, so we also refer, a lot of times you hear me say current term. So f of n equals current term. And f of n plus 1 equals next term. Okay? This again is the language of functions. Okay? And for this very specific expression, equation, or sequence, we can write f of n plus 1 equals 2 times f of n. And this is called the recursive rule. What that means is the f of n plus 1 equals 2 times f of n. All right, this is the next term, next, equals 2 times current. Okay, so if you want to get to what this means is if you want to get to the next term in the sequence and you have the current term, you just have to follow this rule, which says you multiply the current term by 2, i.e. we're doubling it. That's how you would write it. Again, this is the recursive. This is called a recursive equation. Okay. Why is it recursive? Because it builds up, right? You have to have a starting value and you have to know how to go from one term to the next. Okay. Last bit before I cut this off and start a new video for the CYU is learning target number 1. Sequences can be written as functions. Okay, written as functions where the term number is the input, that's n, and the term value is the output. The domain are all positive integers like 1, 2, 3, 4, 5, 6, 7, 8, 9. N cannot be negative. Okay. Explicit rules give equations to find the term value based only on the term number. And we call that the explicit. The recursive, you have to build up to. You have to be given a starting value, point, and then you have to go from one to the next by following the rule until you get to the term number you want. It's easy to calculate, and it's actually easy to write, but the downside is you can't just, if you were given the first term of a sequence and you know you're adding 3 each time to go from one sequence to the next, it's an arithmetic, and you wanted to know what the 100th term is, you would have to keep adding 3 100 times, and it gets cumbersome. So that's why we don't like to necessarily do that. So f of n, okay, explicit rules give equations to find the term value based on only the term number. Example, f of n equals 4n means that each term is 4 times the term number. They're looking right here. Okay. Sorry about that. The recursive form would be this. The new value, or the next value, equals the current value plus 6. That's how you go from one term to the next. f of n plus 1 represents the next term after the nth term. F of n minus 1 represents the previous term as compared to the current term. All right, and that's it. Now I'll do the CYU.